Okay, thank you very much for that introduction. Yeah, let me share my screen here and then I'll start the slideshow. Okay, can everybody see the slide?
Yes.
Good, okay. All right, so thanks for the invitation. As Maria was saying, in a way, this is good because it would have been difficult to for me to go to Athens and give the talk. So I'm very happy to be able to talk about this. And as Maria mentioned, I'm quite happy to have people interrupt because this is a subject that certainly a year and a half, 2 years ago, I knew very little about, and I suspect that most physicists don't know much about it either. So I do want to talk about the spin history of Earth. This is work with my graduate student, Hambo Wu, with Christopher Lee and Kristen Manu, who are two other professors at Toronto. Oh, and I left off the person who started all this, Jeremy LeConte. Oh, well, I got to fix that. He's a professor in Bordeaux. So I'm just showing some data here on the left, which are thin sections of sedimentary deposits from Australia. They're about 900 million years old. And they're tidal deposits, and I'll describe them a bit more later in the talk. And on the right, I'm showing the length of the solar day as a function of the age of the Earth. So the present is over here at 0. Geologists do it this way, right? And the Earth is about 4.56 billion years old. And you can see there's data on this plot going back to 3.2 billion years. So it's quite old data. This data over here is one of these points in here. So I'll describe how this data comes about. Then I'll describe why we think the length of the day is changing. And you can see in the plot here, there's some evidence that the length of the day was roughly constant for about 1 billion years. And I'll describe that in more detail. And that was around 18 or 19 hours. Okay, so I'm going to start off with just a discussion of, hang on one second. Very interesting. Gravitational tides, which is one of the things that changes this rotation period of the Earth. Since you're in a seafaring nation, you're probably familiar with tides. There aren't real large tides in the Mediterranean, but they do exist. And if you go out into the Atlantic, you can see them a lot larger. And this is a paper from then Sir William Thomson. Later on, he was called Lord Thomson and then Lord Kelvin. As you can see here, this is 1882. And the title of this paper is called On the Thermodynamic Acceleration of the Earth's Rotation, but he starts off with the discussion of the tides. He says here, it's long been known, having first, I believe, been pointed out by Kant and more recently by Delaunay, that the Earth's rotational velocity is diminished by tidal agency in virtue of the imperfect fluidity of the ocean. So he's just saying that the ocean tides, which are of course recognized long before Kant or anybody like that, it was recognized by Newton that they were produced by the gravitational influence of the moon. But he didn't realize that the tide wasn't quite at its peak when the moon was directly overhead. That was realized later by Immanuel Kant, that there was a bit of a delay between the moon passing overhead and the tides being at their maximum. And in fact, the tides are at a maximum before the moon passes straight overhead. And that produces a torque on the Earth. So here's an illustration of that. The top picture shows the naive picture of the tides. This is supposed to be the Earth here on the left, spinning around in the direction indicated by the arrow, and the moon orbiting in the same direction. And if that's all that's going on, the moon produces a gravitational pull on the Earth in the center, on the side closest to the moon and on the side farther away. And of course, the tide, I mean, the gravitational pull is stronger on this side than it is in the center or on the other side. So the net result is the moon is going around in an orbit in free fall, but the near side of the Earth is lifted towards the moon and the far side is actually effectively pushed away. It's not pushed away, it's just not accelerated strongly toward the moon as the bulk of the Earth is. And you get a bulge. Now the way I've drawn it here, that bulge wouldn't produce a torque on the Earth at all because it's lined up with the line joining the centers of the two bodies. In fact, the ocean tide has to move because of course the Earth is spinning. And the response of it is delayed in time, okay? Which means that in the sense of the spin, the bulge is actually ahead of the zenith of the moon, as I indicated earlier. So the bulge is on this side is closer to the moon, but it's in the direction that the Earth is spinning. So there's a torque, a net torque. The moon pulls on this bulge and on the bulge on the far side. But of course, this one's closer. So the force here is larger than the force here, and that results in a net torque trying to pull the Earth backwards in its spin. So trying to slow the spin of the Earth, okay? The dissipation actually takes place typically along continental shelves and margins, as illustrated by the red points here. This is a satellite map of where you have a lot of excess wave energy, which is produced by the tides. There's also some places in the middle of the ocean. Here's the Hawaiian island chain. That produces a big dissipation by launching G modes off the bottom of the ocean floor, where the ocean's floor rises up. And the same thing you can see here circled, that's the that's the mid-Atlantic ridge. That also launches gravity waves, and that produces tidal dissipation. So the combination of that produces friction, and that produces this lag in the bulge, and that produces a torque, and that slows the spin of the Earth. Okay, so that's, again, just showing that illustration. All right, well, that's a nice story. How do we know that it's actually true? Well, you can actually measure two things. One, well, I should say, going back to this picture, if you're removing angular momentum from the Earth this way, the angular momentum doesn't just go away, of course. It slows the spin of the Earth, but it goes into the moon's orbit. So it puts more angular momentum into the moon's orbit. And of course, the total angular momentum is then conserved. If you put angular momentum in the moon's orbit, it'll push the moon away from the Earth. So you're taking both angular momentum and energy out of the Earth's orbit, or sorry, out of the Earth's spin, and putting it into the orbit of the moon. So if the day is getting longer, that's kind of hard to measure directly, although I'll get to it in a second. It's a little easier to measure the distance to the moon. The easiest way to do it is by astronomical observations. You just check the mean motion of the moon, the time it takes to go around, or alternately the integral of that, the location on the sky as a function of time. And astronomers have been doing that basically since, well, before Kant made this suggestion. And the moon is being, it's called accelerated, because as it moves farther away, the orbit takes longer. So the moon doesn't get to a location on the sky as fast as you think it should. And that's actually been measured for a long time. More recently, it was just directly measured. The rate at which the moon is moving away from the Earth using the Apollo astronauts mirrors they left behind on the moon, the surface of the moon, these corner cubes. And then people have been bouncing lasers off of these corner cubes ever since. And from that, you can measure the rate at which the moon is moving away from the Earth. It's about 3 centimeters a year, okay? And that agrees with the estimates from the earlier astronomical measurements. It also agrees with the estimates of the amount of dissipation in the tides on the Earth, okay? You can go back in time to see, you know, has it been moving away from the Earth over a long period? So this is showing a lot of lunar and solar eclipses as recorded by various people going back about 2,000 years. You can see these are the green circles are Babylonian lunar eclipses. The pluses are Chinese lunar eclipse measurements. The blue crosses are Babylonian solar eclipses and so forth. I like to point out that most of these are, the older ones are not from either Europe or North America, because basically there were no civilized people in those places at the time. Civilized meaning who recorded astronomical measurements. And again, this is consistent with the currently measured rate of recession of the moon away from the Earth. And this is not a measurement, of course, of the recession of the moon. This is a measurement of the spin rate of the Earth. So it's the change in the length of day, the cumulative length of day in seconds. So over that time, it's 20,000 seconds. That's a clearly measurable amount. Now there's one difficulty with this story, and this plot's just showing that. This is showing the distance between the Earth and the moon as a function of time in what the geologists call eons, or billions of years. And here it is today, okay? And if you go backwards in time, it gets closer to the Earth, and then it comes down here and it actually hits the Earth about 1 billion years ago. So if you have the current rate of dissipation in the ocean tides occurring over the last 1 billion years, the moon would have, if you run the experiment backwards, it would have run into the Earth. And we know that's incorrect, because we have, well, evidence, of course, that the Earth is 4.4 5-6 billion years old, and we have rocks that are 3.5 or thereabout billion years old. So we know that something like this probably didn't happen. And we now have, of course, moon rocks, which are dated to be 4.4 billion years old. So there's something wrong with this story. And the obvious thing there is that the dissipation rate in the oceans may change with time. There are other types of evidence. This is one form. This is a thin section from the shell of a clam. The name here is given here in Oregon. And you can see clams, they live in water in the tidal regions. And as the tides go in and out, it affects the growth rate of the clam. And that actually gets recorded in the shell. So that's what's being shown here. These are the daily growth rings. You can see there's a dark line and then a sort of a slightly less dark line, and then again a dark one and a slightly less dark one. Those are consecutive diurnal, semi-diurnal tides, right? You have a high tide twice a day. One is larger than the other. That's why it goes light, then dark, then light. Okay. And then you can see that in this region, the clam seems to be growing rapidly. And in this region, it's not growing so rapidly. And that's due to the difference between what are called spring and neap tides. When the moon and the sun are aligned, you get very large high and low tides. Okay. But when they're at 90 degrees to each other, or when they're on the same side of the earth, but when they're at 90 degrees to each other, the tides are not quite as high. So the really large high and low tides are called spring tides. That's these large ones here. That leads to these large growth rings. And the smaller regions where the tides, this top part is just a tidal chart, I should say, the height of the tides. In the neap tides, the tides are quite a bit less extensive, and the clams don't grow as well. They're filter feeders, so they want a lot of water going by so they can get their nutrients in. And if the tides aren't moving very much, you don't get as many nutrients, so you don't grow as well. Okay. So this is in 1970. This is just a way to compare the shell to the actual tidal measurement. So in fact, they are recording the tides, so that's good to know. So now you just go find a fossil clam that's 500 million years old, and you can measure the tides that way as well. Okay, so that people have done that, and I'll show some data from that later. Now, of course, clams and anything sort of multicellular, didn't grow until about 500 million years ago. So if you want to go farther back in time, you have to look at geologic data. So this is another record of tidal deposits, as I showed you. This isn't from a clam. This is just sediment laid down at the mouth of a river. And here, the light and dark bands in these various plots here are when the tide is flowing rapidly, when it's neither high nor low, but when it's ebbing or flowing in and out, you get a lot of sand deposits. That's what the lighter things are here. When you reach the high tide, of course, the tide stops flowing, and then the mud that's normally kept suspended drops out, and you don't get any sand because there's not enough velocity to carry the sand. So that's why you get a difference between light and dark bands here. And you can see the same sort of variation you saw in the clamshell, where you have a fairly dark band, then a lighter dark band, then a fairly dark band again. It's a semi-diurnal tide, 2 tides a day. And then the different widths here correspond to spring tides where it's wide, and the narrow ones are neap tides. Okay. So this is again from a rock that's about 900 million years old. And you can work out from this the number of days per month directly. You just count the number of days in here between these dark bands. That's the number of days between a spring tide and a neap tide, which is 2 weeks. And then you count for the next one, and that gives you the month. So that gives you the number of days per month. Now, in the last 15 or 20 years, people have worked out yet another way to measure both the length of the day and the length of the lunar month. And that's from geologic deposits. So I'm showing here a road cut, or several road cuts in China, and it's called the Zimaling Formation. And these are not on the time scale of tides, not daily deposits, but these are over, as you can see here, 1.39 to 1.384 billion years. So over tens of millions of years or thereabouts. And they actually record climactic variations produced by different amounts of sunlight hitting different latitudes on Earth. So these are following essentially what are called Milankovitch cycles, for those of you who've heard of that. And from that, you can also work out both the precession rate of the Earth around its axis due to the moon pulling on the equatorial bulge of the Earth. So that gives you the precession rate of the Earth. And that tells you the spin rate of the Earth and the distance to the moon. So this is just showing some data, showing how you quantify that. You measure various ratios of types of elements. And you can look at that periodic cycle and you can compare that to numerical integrations of the solar system. And that'll tell you with high precision what the age of this deposit is. Sorry, what the frequencies of these deposits are. The ages, of course, you work out from radioactive dating in regions where you have, say, ash layers. I won't discuss that too much, I'll go on. So if you put together that kind of data, you can make plots like this, millions of years before the present, and the distance between the Earth and the Moon. So here's today. This is going back in time to, as is on this plot, to 2.5 billion years ago, labeling different kinds of deposits. These are the tidal deposits I was showing you. These are some other ones. These symbols in here are, they're called bioarchives here. They're like the clam shells that I was showing you. And then the most recent data is given by these blue ones, which have quite a bit smaller error bars. Okay. And the idea here is it's telling you, how far away was the Moon back to, well, up to 2.5 billion years ago. So it was quite a bit closer in the past. And that's a fairly direct measurement. So here's another plot that I made with similar data, showing the same behavior. Now here I put on 3 lines, and I'll just describe quickly what they are. I won't describe how I got them. There are 2 models where I've used a Monte Carlo calculation to calculate the best fit to the data. And the 3 models are this green dot dash line, which you'll see in other plots. That's just using a model where we only include the effects of the solar and the lunar tide. So the solar tide doesn't make much difference, but it's easy to include. So this is the best fit to that data, with the constraint that the Moon has to be at least 4.4 billion years old. Okay. This black solid line includes both thermal tides and gravitational tides. And that's the best fit model. And then this dashed red line is taking that best fit thermal model, integrating it back from 4.5 billion years ago to the present, but ignoring the thermal tides. And you can see it produces an orbit of the Moon, which leaves it much farther away than the Moon is currently observed to be. And I'll explain why that happens in a bit. Okay, now I've mentioned thermal tides, but I haven't actually told you much about them, so I'm going to talk about them now. So thermal tides have been known, as I said, for well over 100 years. And here's an example of a measurement from Batavia, which is now called Jakarta. And this is back in 1919, but the records go back to the 1800s. I'll show you some of them. And this is just a recording of the barometric pressure, right? A barometer is just the way these measurements were made. You take a bunch of mercury, you take a tube and invert it where it's full of mercury and leave it sitting in a pool. And the atmospheric pressure will change. Now change the pressure at the top of your pool of mercury, and that changes the height of the mercury in the evacuated tube. And you just record that over the day. So you can see here, this is over, well, there's the 5th, the 6th, the 7th, the 8th, and the 9th. So what is that, 4 days? And the pressure goes up and down, as you can see here, twice a day. Okay, so this is midnight right here. And this is noon. So there's a pressure minimum you can see here around 4 o'clock. And there's another pressure minimum here at around, what is that, 8 in the morning, I guess. Okay, and that's what's called the thermal tide. And the reason it's occurring here is because in the afternoon, as you know, that's the hottest part of the day. The sun is heating up the atmosphere. And as it heats up the air, that tends to raise the pressure of the air. Well, the air is going to move away from that hot spot. It tends to move horizontally. It's hard to move the air up against gravity. So it moves horizontally. But if you move air horizontally, if you're down on the surface of the Earth and you look up, you'll have less air above you. And of course, this barometric pressure is just exactly the weight of all that air above you per square centimeter or whatever. And that's what you're measuring here. Normally, it's around 760 millimeters of mercury, but it goes up and down, as you can see here, by about a millimeter of mercury, maybe a little more. And of course, it's the biggest signals, as I said, 12 hours. There's also a 24-hour period in here, which is a little harder to see. And that kind of puzzled people for a while. But you can imagine the sun is up not for 24 hours a day, it's only up for 12 hours a day. So it's not surprising that you get a 12-hour period in here from that point of view. They also show in this plot this variation at Potsdam, which is of course much farther north. And if you measure for a long time and use modern techniques, you can actually pull out this semi-diurnal signal out of there as well, but it's harder to see. What you're mostly seeing here is weather. That's what causes this. Okay. So here's more from that paper from Lord Kelvin, and here's his image of the semi-diurnal tide. And here's the sun up here heating the Earth's atmosphere. Here's the center of the Earth. The Earth's rotating this way. And he knew from the data that there was a minimum in the pressure in the afternoon and a maximum here at 30 degrees before noon. And from the picture, you can see it looks a lot like that the ocean tide picture, but with a 30-degree lag here. This bulge is closer to the sun than that bulge. So it gets pulled harder than this bulge does. That tends to pull the Earth's spin forward in its orbit. It tends to increase the amount of angular momentum in the Earth, the opposite of the lunar tide. And that would cause the length of day to decrease. Okay. And he was looking at data, in this case from January of 1880, going back. The data, as you can see here, was from 1841 to 1845, 1837. So this data was available in 1880 to Lord Kelvin and had been recorded even before that. And they had actually worked out the diurnal and the semi-diurnal constituents. Of course, in this case, in inches. These were the quarterly journal of the Meteorological Society, and they mean the British Meteorological Society. So the variation here is in basically a few hundredths of an inch. Okay. Or as Kelvin says, getting quit of the intolerable British inch, it's about 8 millimeters of mercury. Okay. And it varies with latitude fairly strongly, cosine squared. So it really is down in the tropics where you see this. Okay. So here's a modern day global circulation model. This is from the paper that I mentioned earlier by Jeremy LeConte, who was the postdoc at CETA, showing the prediction of the amplitude of the semi-diurnal tide. So these bright white spots are up around a little over a millimeter of mercury actually, and it's mostly confined to the equator and up in the northern latitudes, right? I mean, Athens is somewhere in here. It's not too strong. So it's hard to see up in northern latitudes or southern latitudes. So here's a plot showing both the semi-diurnal tide, which you just saw. Here's the diurnal tide, which is not as strong. And then here's the phase, which is about 150 degrees, which is this, 10 o'clock, 4 o'clock type phase that we were talking about, or 8 o'clock and 4 o'clock. Okay, now this prediction here can be compared to actual measurements. This is from Chapman and Linzen. And you can see that here it's 120 corresponds to 1.2 millimeters of mercury, okay? And it falls off rapidly. So up here, again, in the Northern Hemisphere, you're talking about more like 20 millimeters, sorry, 0.2 millimeters of mercury. So it's quite a bit smaller, a factor of 6 smaller compared to the tropics. Okay. All right, so now I'm going to talk a bit more about the theory. So are there any questions about that data or about the physics of the thermal tides that people have? It's all perfectly clear so far. Well, that's good.
I don't see any questions so far.
Okay, good. All right, so now, so you can see there's observational data that the distance between the Earth and Moon has been varying. The length of day was shorter in the past. That's what those eclipse measurements were showing. The tidal measurements show the same thing, that the length of day was substantially shorter in the past. Again, I'll show more data in a bit here. I want to talk a little bit about the theory. So I've said that the sun heats the atmosphere, pushes air away from the hot spot, and that produces a variation in the barometric pressure. And I've also shown that it goes up and down at any given location twice a day. What is it that's causing this? And well, I mean, that's the basic physics, but what I want to argue now is that variation in the pressure of the atmosphere, that'll depend a lot on the spin period of the Earth. And the reason for this is pretty straightforward. So this is a nice bit of physics, right? If you imagine that, if you're sitting on the surface of the Earth, you see the barometer going up and down. But if you're looking out at the solar system from above, you can see the sun here and the Earth here, and the Earth spinning around. And that bulge will be like in that picture from Kelvin. Seen from above, that bulge won't be moving. It'll just be sitting there. The Earth will be spinning underneath it. Okay, so this thing looks like a wave traveling around the Earth from east to west. Okay, well, it's a wave, but it's in a periodic system, right? The Earth is a sphere. So you can imagine if you got a traveling wave in something with periodic boundary conditions, you wouldn't be surprised to learn that there's a resonant mode or resonant modes in that system. And the basic one is going to be just the mode that corresponds to a time period where the time for the wave to travel around the circumference of the Earth is equal to the length of the day, because then you'll be forcing the wave at exactly its natural frequency, right? Because if you take the circumference of the Earth, 2 pi times the radius, that's how far that wave has to travel around the Earth. The length of time that'll take is 2 pi times the radius of the Earth divided by the wave speed, which is not quite, but it's pretty close to the sound speed in the air, the mean sound speed. And that gives you a period of around, if you just do it the way I said it, about 24 hours. If you do it a bit more carefully, it's a bit shorter than that. It's about 22.8 hours, you can see right here. So this is a measurement, a prediction from one of these global circulation models, which I mentioned, LMDZ. This one's actually from one called Planet Simulator or PLASM. This is the pressure variation in essentially millimeters of mercury as a function of the length of day or the spin period of the Earth. So today we're sitting here at 24 hours and we're driving this mode at a period which is a little longer than the resonant period. If the Earth were spinning faster, we'd be driving that same mode with a shorter period or a higher frequency, and we'd actually get a bigger response. If we had the Earth spinning even faster, say 20 hours, we'd be on the other side. So this, for those of you who remember your freshman physics, this is a classic signature of a linear damped driven harmonic oscillator, which is exactly what this system is, right? You've got the Earth's atmosphere is carrying a wave. That's the harmonic oscillator part. It's damped because there's friction in the air, which we don't understand actually. And it's driven by the heating of the sun. And it's also linear because, as I said, right, the pressure at the surface of the Earth is about 760 millimeters of mercury. And the amplitude of this wave is about 1 millimeter of mercury. Okay, so that's a very linear system. So that's fairly straightforward. What we were doing there is just an experiment where we just changed, in this case, we changed the gravity, surface gravity of the Earth. And it didn't change the period, it changed the amplitude of the response. And the reason for that is if you increase the gravity of the Earth, you make the air, you pull it down harder towards the Earth, okay? So that effectively increases the pressure. And if you increase the pressure, molecules that produce opacity in the air, they hit each other harder and faster because the pressure is higher. And that produces what's called pressure broadening. You get more opacity in the atmosphere. And that makes it capture the sunlight better, which increases the amplitude of the pressure variations here. We did this to check whether this mode was a gravity wave or a pressure wave. If it's a gravity wave, you change the amount of gravity, it'll change the frequency. And you can see here the frequency doesn't change. So it's not a gravity wave. But if you change the temperature, in this case, we just changed how bright the sun was, that changes the mean temperature of the Earth. And that, as you can see here, changes there's this resonant period. So that tells you that it's really a sound wave that you're talking about. You can also see that the amplitude changes. Okay, so that becomes important later. So I'm not going to go through much math, but let me just show you one slide with some math on it. You can describe this system with a combination of the momentum equation, which I've reduced to one dimension here. So this is the velocity of the air. This is the pressure of the air. And this term is the damping term that I mentioned. There's some friction. This is the energy equation. So pressure is energy per unit volume. So this is the change in the energy in a given Lagrangian region. It's normally 0, but in this case, we've got a term here, it's called dq dt. That's just the heating from the sun. Okay, that's the heat coming in from the sun. And if you combine these two equations, you get this equation. Okay, I've eliminated, in this case, the u variable. So I take two first order equations with two different variables and reduce it to a second order equation with a single variable, the pressure. Okay, and you can see it's d squared p dt squared minus the sound speed squared times d squared p dx squared. That's the wave equation. You should recognize that. This is the damping term that comes from this one. And this is the driving from the solar driving. Okay. So now I want to discuss briefly what the solar driving looks like. Where does it come from, right? I won't go over this, so I'll skip over that. So because people have been interested in climate change, there's been a lot of research on this over the last couple of decades. So here's how the atmosphere is heated. Here's the sunlight coming in. The number you may remember is 1,360 watts per square meter, but that's at the equator. If you average it over the whole globe, you divide by 4 basically. So that's 340 watts per square meter coming in. Okay. And you get reflected solar light going out, you get 100 watts per square meter going back out. Okay, and a lot of that comes from bouncing off of clouds. Some of it comes off of surface reflection and other things. Okay. But that means 240 or whatever does get down here to the surface. And there hasn't been much absorption yet. Okay, so here they give you what the atmospheric absorption is directly out of the sunlight coming in. It's around 75 watts per square meter. So a small fraction of this. The other main source, actually the biggest source, is given right here. It's called latent heating, 88 watts per square meter. And what that means is, particularly near the equator, you're evaporating water out of the ocean. That water vapor goes up in thunderheads, storms, and when it gets high enough, the water comes out of the vapor, condenses, and you get clouds. These are thunderheads, and that dumps a lot of energy into the atmosphere at that height, and that's called latent heating. And then the last part is this sensible heating here, which is just the infrared radiation from the ground going out. And of course, this stuff is trapped, this stuff in particular, by greenhouse gases like CO2. So that's the one that we're currently messing with, changing the sensible heating. The latent heating doesn't change that much. Okay. Let me move along here. Of course, as I said, this leads to a resonance in the atmosphere. And I was showing that earlier in these plots. That's showing you the resonance. That's just the pressure. Now, of course, when you're right exactly at resonance in a harmonic oscillator, there is no phase lag or lead. So you get the maximum pressure perturbation, but in fact, you don't get any torque because the bulge is exactly lined up. So I'm just plotting here the torque as a function of the length of day. Okay, and you can see it starts off, if you're long of the resonant period, you get a positive torque. You go through 0 right here at around 22.8 days, and you get a negative torque on the other side. That's the classic signature of a harmonic, damp-driven harmonic oscillator. Here's an expression for the period of that wave. It's the square root of, this is basically 2 pi r. It's squared because it's inside a square root, and then divided by, this is the inverse of the sound speed. And then there's this parameter here is basically a constant of separation in the fluid equations. Okay, so then to describe the behavior of the spin of the Earth and the Moon, it's pretty straightforward, right? There's the total angular momentum of the Earth in its orbit around the Sun, and that's affected by the solar tides and by the thermal tide. There's the spin angular momentum of the Earth, which is also affected in exactly the opposite sense by the thermal tide, and again in the opposite sense by the solar tide, and of course by the lunar tide. And then there's the angular momentum of the Moon's orbit around the Earth, which has, of course, the opposite sign from that torque. And if you add all three of these up, of course, the right-hand side adds up to 0, so the total angular momentum of the system is conserved. Okay. Now, if you don't have a thermal tide, the angular momentum of the spin of the Earth plus the Moon also is nearly conserved, because this term is much bigger than either of these two terms currently. This is about 5 times the solar tide currently, and in the past it was even a larger ratio. In the past, this torque was much larger because the Moon was closer. So if you add just these two and ignore the thermal tide, you expect that the sum of those two angular momenta to almost be 0, I mean almost be constant, and it is nearly. But the thermal tide changes that. Okay, So I've already showed you this plot. This is showing the data on the semi-major axis of the moon over time. And these three plots are the ones I said. This is just the tidal torques from the sun and the moon, the gravitational tides. This black curve is all three tides. And this red curve is using that same initial condition as for this curve, but ignoring the thermal tide. Okay. So the reason that the moon in this case moves so much farther away from the Earth is because when you calculate the evolution of the Earth using the thermal tide is putting angular momentum into the spin of the Earth. And that makes the Earth spin more rapidly than it would if that tide were not present. If the Earth is spinning more rapidly, it turns out that the ocean tides they don't have as much dissipation at high spin periods. But as the Earth spins down to longer and longer lengths of day, you get a much stronger interaction between the moon and the Earth's oceans. And so you get a much stronger lunar tide. And that's what's happening here. In this case, this black curve is starting with a lower total angular momentum between the Earth and the moon. And so for a given, if you just have the lunar tide, the length of day at a given age will be much longer than it is currently. And that in turn leads to a much stronger lunar tide, which causes the moon to move a lot faster outward. And that's what's going on here. Okay, so here are two possible torque histories. The one on the left is including the thermal tide, and the one on the right is ignoring it. The current torque is here, measured today. This is actually a best fit model, and you can see the torque's a little bit higher than the currently measured one. And basically that's not an error. That's because the one today is a little bit lower slightly than the average over the last few 100 million years. And of course, this thing's averaging over hundreds of millions of years. Okay. But this one gets the moon at the right location today. This plot, you can see there's a lot more variation. Okay. But it ends up with roughly the same observed lunar torque. The green dashed line here is the thermal tide. And you can see what's going on here. Early on, long time ago, the Earth was spinning very rapidly, and the torque from the thermal tide was negative. I've reversed the sign, relative sign of the lunar torque here is actually negative all the time, but I showed it as being positive so you could compare these two more readily. Okay, so the lunar torque is always of one sign, but the thermal torque is not. It started out being the same sign as the lunar torque, but around 2.2 billion years ago, it switched signs. We went through that resonance. The length of the day went through the thermal resonance. Okay. So what that does is it changes the evolution of the number of solar days per month. So this data shows you the number of days per month over time. And you can see there were 26, 27 days per month back here 3 billion years ago. And the number of days per month went up rapidly and then dropped down again. So that's the signature in the data that you pass through this resonance with the thermal tide. And you can see the same thing in the length of day. So here's the length of day in hours versus age. And it's roughly flat in the data through here. And there's a lot of scatter. The data isn't great, but the ones with the small error bars indicate that it's roughly flat here from about 2,000 million years ago to about 1,000 million years ago for 1 to 2 billion years. Okay, now there's one other thing you can do with this bit of data. I still have about 10 minutes, I think. Well, this just shows, so from that best fit model, this black curve, I should say again, this is the lunar and solar tide only, no thermal tide. This is all three types of tides. Now these curves, the green curve and the red curve, are roughly constant angular momentum in the Earth-Moon system. And you can see the data does not follow either one of those curves. This is telling you that the amount of angular momentum in the system between the Earth and the Moon is not constant. There has to be a third source of torque, which we're interpreting as a thermal tide here. So from those plots, as I said, that's the best fit, that black curve using a Monte Carlo approach. You can infer the resonant period of the Earth's atmosphere as a function of age. So that's what I'm doing here. So these black dots are just the priors that we put in. We put in Gaussian priors at roughly the current resonant period of the Earth, 22.8 hours. We made the priors smaller at these two times, 600 million years ago and 2.2 or thereabouts. And the reason for that is that we know at those times there were global glaciers occurring. Possibly a snowball Earth, it's not clear, but there were glaciers near the equator. So you know that the temperature of the Earth's atmosphere had to be below about 10 degrees on average. And so that gives you a pretty tight constraint. The rest of the time, we don't know that much about the temperature, or the resonant period, so we just left it as at the same period, but gave it somewhat larger error bars. But you can see then the best fit model says, no, that's not right. The period here, had to be much shorter back around about 1.5 billion years ago. And of course, the data that's telling you that is this data here. This is saying the length of day here was about 19 hours, which is what this thing is saying. This is the period being 19 hours, the resonant period. And so the argument is that the length of day here is telling you that you're in this resonance, and that resonant period is 19 hours. Okay, we can go one step further. From that, remember I said that the period is 2 pi times the circumference of the Earth divided by the sound speed. We're reasonably sure the radius of the Earth didn't change, so the sound speed must have changed. And you can use that to infer the temperature. So that's what we've done here. Now today the temperature is around 15 degrees. So our best fit model gives you about 20 instead of 15. Okay, and the shading shows you the errors supposedly. But it says back at about 1.5 billion years ago, the temperature was up above 50 degrees Celsius. That's the average temperature of the Earth. The equator would have been even hotter than that. So that's an incredibly high temperature. But there is actual evidence that the temperature was elevated at the time. And part of that is, remember I said that there were ice ages here at around 600 or 700 million years ago, and here at 2.2 or 2.3. There were ice ages over this whole range back here, going back even earlier than 4 billion years. And of course, we've had ice ages ever since this 600 million years ago to the present. They come and go. They don't last very long, but they're constantly there. But it's been known for a long time that there's this range of time in here, about a billion years, where there isn't any evidence for large-scale glaciation. So that's consistent with this temperature. All right. So I'm going to describe my conclusions here. So I think I've shown that both gravitational and thermal tides are readily measured in the geologic record. And currently they affect the Earth's spin in the opposite sense. The lunar and solar tides tend to slow the spin rate of the Earth, whereas the thermal tides tend to increase the spin rate of the Earth or shorten the length of day. In the Archean, which is like between 4 and 2.5 billion years ago, the dissipation rate of the lunar gravitational tide and that torque were lower than they are today. Okay, and at the same time, the thermal tidal torque was stronger, and it added a significant amount. It turns out, if you look at it, it's a few percent of the angular momentum, the current angular momentum of the Earth-Moon system, was added in by this thermal tide. And of course, that angular momentum came out of the orbit of the moon, the Earth around the sun. So the total angular momentum of the whole system stayed constant, but you're feeding in from this really big reservoir of angular momentum, the Earth's orbit, into the spin of the Earth directly. Earlier on in the Hadean, the thermal torque was removing angular momentum from the system. And so that resulting excess angular momentum is in fact detectable in the geologic record. And that's what that data I was showing you says. So thank you.
Thank you very much. It was very interesting and you were perfectly on time. So let's see if there are any questions.
Yeah, can I ask a question, Maria? This is Petrosiano.
Yes,
very interesting talk. I'm not really sure I understood. During snowball period, do you get indirect indication for snowball periods from your data?
Not from the data directly. No,
huh?
not directly from our data. You do not. We put that in as a prior, if you're familiar with that terminology.
Yes.
Yeah. So no, our data doesn't tell you. Let me see if I can find that. Hang on.
At this period, you would expect essentially zero contribution from the ocean tide.
No, not necessarily, right? I mean, if you have a snowball Earth, the oceans aren't frozen solid. There's only an ice layer on top of the ocean. So you still get a tide from the ocean, you still get a contribution from the ocean tides, right? Because
from internal gravity waves or something, yeah.
Well, you'll get it from internal gravity waves, but you also get it from any continental shelves. Yeah, that's right.
Okay. Now,
but to answer your question, that information that there was a snowball Earth is not coming from the data that I'm showing you. That requires other information. Yeah.
Okay. And also, you assume that the dissipation rate of the thermal tide is more or less the same in this model from what I saw.
No, sorry. So I should have made that more clear. If you assume that it's roughly the same, again, you have this problem that the moon integrated backward runs into the Earth only about 1 billion years ago. You had to have a tidal Q that was a higher quality factor, which means less dissipation in the past. And we use a simple ocean tide model to model that. And I can describe the model really briefly to you. Basically, it's a model where you assume that roughly half of the Earth is covered by an ocean, the idea being the Pacific. And you force that ocean with a given driving. And of course, the ocean has normal modes of its own, the water sloshing back and forth. And so there are a lot of resonances in that ocean. And if you sum up the effects of all the resonances and then plot them as a function of the spin period of the Earth or the frequency of the forcing of the tide, you'll see that if the spin period of the Earth is shorter, if the day was shorter, I should say, if the period was shorter in the past, you don't get as much dissipation as you do today. And in fact, if you go forward in time where the length of day gets longer, you start to run into a really strong resonance in the not too distant future, meaning tens or hundreds of millions of years, where you'll get a lot more dissipation because the size of the ocean gives you a resonant period, which matches with the forcing from the moon right now. Now, of course, the problem there is, well, that's great, but the continents don't just sit where they are. They move around with time. So the size of the ocean varies with geologic time. Now, people have actually tried to model that recently. I mean, people can actually do hydrodynamic models of tidal dissipation with real bathymetry of the Earth's oceans currently, and then get a pretty good estimate of the dissipation rate. And then the next step is to take the locations of the planets that geologists infer from, of the continents that the geologists infer, and then try to run those same models in the past. And people have actually done that going back 500 million years. So it's pretty impressive. Now, you don't have to believe those estimates, of course. So what we've done is taken this really toy model, and we only had to slightly adjust the overall dissipation rate to get it to so that the moon actually did form 4.5 billion years ago. That was one of the constraints we put in. The moon has to be at least 4.4 billion years old because we have moon rocks in hand that are that old. So we have a model which is a well-defined analytic model for the Q factor. I can give you the references if you want offline. And then use that as part of the Monte Carlo calculation. We just adjusted that Q up and down slightly by like 10 or 20% to get the moon to be old enough.
Yeah, but I was wondering about the thermal tide as well, in the sense that, you expect the thermal tide to depend very much on composition, the excitation, because of the absorption type of properties.
Yes, absolutely.
And so do you get any data essentially about the effective excitation and the
so let me tell you what the data
dissipation as well?
That's right. Yes, you do. Okay, so this blue line here in this plot I'm showing, if you can still see my screen.
Yes, I can.
That is inferred by the model from the data. Okay, and the data, as I said, that's really constraining that is there's two types. There's this length of day data and the number of days per month. The number of days per month gives you, it's a ratio, right, of the spin period of the Earth to the spin period of the moon. If you know the length of day, which you do independently from some of the other data, then you can infer from that the distance to the moon, or alternately, you can just measure that directly from this data. Again, it's another type of geologic data. So you have 3 different ways of measuring 2 quantities, right? All right, so from that, you get, if you assume the thermal tide is operating, okay, then you'll get this measurement of the resonant period in the atmosphere. So as you say, that depends on the temperature of the atmosphere and on the composition. Now, it turns out that to get this big of a variation, this is from 23 hours a day, although in the model it's only 22 and change, down to 19, that's a fairly large change. There's no plausible composition change that'll give you that big of a change in the period. The bulk of that has to be coming from the change in the temperature. So this is telling you something about the temperature history of the Earth's surface. Now, there are assumptions that go into this. So you mentioned one. One is, what is the quality factor of the Earth's atmosphere due to this mode? Okay, and that we infer from the model. So I didn't show you the plots of the output from the Monte Carlo, but again, I can, if you want, I can send you. We have a draft. It has to have a fairly high quality factor to be able to cause this resonant lock. You've got to have a quality factor in the Earth's atmosphere of around 80.
Cool.
If you look at analytic calculations from the 60s, excuse me, people calculated it was somewhere between 40 and 100. So 80 is plausible. So there's actually a constraint from the data on the quality factor of this resonance in the Earth's atmosphere. On the other hand, if you look at our global circulation models, they also give you an estimate for the quality factor, and it's more like 10. Okay, and I take that to mean, in fact, that we don't have good enough resolution in the global circulation models to calculate that dissipation properly. Right? There's artificial viscosity put in to these global circulation models. That's probably not the source of it. We varied that by hand, but I don't think it resolves the turbulent eddies that are generated by these flows. This causes a wind back and forth, right, at the surface, and I don't think that's calculated properly in these models. So yes, you can learn about the dissipation in the atmosphere. Now the heating is a different question. To get a big enough response, and to get the biggest thing is to get a high enough temperature, you have to have a lot of carbon dioxide in the atmosphere in the past. That's one of the conclusions coming from this. There had to be like close to 1/10 of a bar of CO2, even 1 billion years ago, 1.5 billion years ago. There's pretty good evidence that back here, there was easily a 1/10 of a bar of CO2 in the atmosphere. But this is saying that even at 1.5 billion years, that you had to have about 1/10 of a bar of CO2 in the atmosphere. So that is coming out of this calculation, yeah.
Interesting, thank you. I would have, if I can make a suggestion, I would think that most of the dissipation, the thermal dissipation, comes from the breaking of gravity waves up in the mesosphere.
That's quite possible. I agree. Yeah. And then the question is, right? So we're using, so plasma is really simple. It only goes up to the the beginning of the stratosphere, and it's and you're only getting, normally you're only getting like.
So you would get reflections.
You would get reflections, yes.
Okay, that's a problem.
Well, it turns out probably not such a big problem because it's high enough up that so the other model we're using is LMDC.
Yeah, but you don't have a good good sense for the dissipation. The dissipation is absorption.
You'll get no good. No, I agree with that. You won't get a good sense of the dissipation. It won't affect the period that much, is what I was going to say, because that is basically causing reflection, as you say, by itself. The temperature change. So LMDC does go higher, but it doesn't. I don't think it does a much better job of getting the dissipation again, because the resolution of these codes is not great. It's maybe 10 or 20 vertical cells, and it's just not enough to get the dissipation right. I think we check that by changing the resolution, and we do see that the dissipation, the Q changes, not by that much. I would have hoped it would like double from 10 to 20. It doesn't. It only goes up like from 10 to 15 or something. But it does depend on the resolution. So that makes me think that that those results from the GCMs are not reliable.
Okay. Thank you very much.
Yeah.
Great talk.
Thanks.
So
Georgios, you have your hand up. Yeah.
Yeah. So I have one question, and actually very similar to one by Kimon Chilias. So Kimon is asking if you have taken into account the changes in the solar activity, like the 11-year cycle, and if this has been taken into account for the thermal tidal model. And I also would like we know that the solar activity changes through the year, so long-term changes in the solar activity.
Changes.
Yeah, the luminosity changes with the year. Has things been?
No, so the variations in the activity have not been taken, and no account has been made of those, the change in the activity. That may, well, it almost certainly does affect the temperature of the Earth. I mean, it affects the amount of cosmic rays that reach the Earth's surface, for example. So that changes the amount of clouds in the atmosphere, and that's been noticed, but we didn't include that in here. That, I believe, is a fairly small effect. The other question you raised, though, is, over geologic time, I mean, this is a reasonable fraction of the age of the sun, right? And the sun was actually dimmer back 1.5 billion years ago by 10%. It was 90% of the current luminosity. That we did take into account, okay? And so it's really striking that if you believe this plot, right, the temperature was 50 degrees Celsius on average, back at a time when the sun was 10% dimmer. And that's what's driving this claim I made that you had to have a lot of CO2 in the atmosphere. So we tried various people, this problem, right, never mind this estimate, just think, okay, so today the temperature is like 15 or whatever it is, averaged over the Earth. Well, you go back to the Hadean, where it was supposed to be hot as Hades, okay, but it was, only 75% of the sun's luminosity. It actually should have been really cold, should have been temperatures like this, okay. But we know there was a liquid ocean at the time, and there are ice ages back in this time, but they're intermittent, right? They only last for a few million years at most, and most of the time there aren't any global glaciers, right? So the temperature had to have been up here around 15 or 20, or maybe even higher, even though the sun was 30% dimmer. So that's called the faint young sun paradox. So the resolution of that is pretty clearly that there was a lot more CO2 in the atmosphere in the past, and there is evidence for that. Okay.
And methane.
Methane, so yes, people like methane as a greenhouse gas. My impression is from my running these GCMs a lot is that it doesn't have as big an effect. I can show you, let's see, here's the paper right here. I didn't put it in the talk because it's more for the experts, but we obviously have an expert in the audience. Okay, so here's some of the Monte Carlo stuff. Oh, well, they're just showing you like a corner plot and our run. So yeah, we did Monte Carlo. But this plot here shows, this is for LMDZ as a function of time before the present. So these are various compositions. And what you're seeing here is that, pick a composition like this one, which has it's a 1/10 of a bar of CO2. I'm asking for a total surface pressure of 2 bar and some methane. So back at 1 billion years ago, the temperature, according to this model, was about 45 Celsius, so pretty high. But you go back with that same atmosphere to 3.5, 4 billion years ago, the temperature was down here just barely above 10. Okay, and then these other ones down here are even cooler. They would you'd have ice all over the whole planet. All right, and this is using 2 millibars of methane, but you can see the difference between let's try these two here. This is a 1/10 of a bar of CO2, 1 bar total pressure, and then a difference between 2 and 10 millibars of methane. So that's this red and the pink. So the pink is higher. The methane does make a difference, you can see, but it's only like sort of 2 degrees. Okay, and we really want a change from like 15 up to 45. That's a 30-degree change. And you need a combination not just of CO2, but you also need more pressure broadening. So that's why we were trying models with more total pressure.
What about the vapor content?
The vapor content helps a little bit, right? Because at these high temperatures, you're going to cause a lot of evaporation. And because you got a higher temperature, the saturation vapor pressure is higher. But it helps a little bit with the greenhouse effect, but not a huge, it's not a big contributor. Yeah. So yeah, we're kind of desperate. I mean, I'm claiming in this plot, you need 2 bars total pressure. Well, probably it was nitrogen. There's plenty of nitrogen in the rocks, sedimentary deposited nitrogen, that it could have come out of the atmosphere. And people have suggested this, of course. We're not the first people to suggest the higher nitrogen pressure, but people don't generally believe it because the data for it isn't very good. This is another piece of data I would claim that's saying, in fact, really, if you want to get these high temperatures, if you believe our results, then you probably had to have more nitrogen in the atmosphere in the past.
Thank you. We have one more question by Marco. Marco, would you like to phrase your question, or would you like me to read it? Is Marco still here? Okay, so Marcus is asking, I will just read his question. He says, great talk, and as far as I can understand, thermal tides are transferred sun's momentum via radiation. Could there be a friction line like momentum transfer from the interaction of the solar wind and the magnetic field? Is this interaction considered and included in the energy dissipation?
Okay,
and
so go ahead.
And if this can, and based on that, how certain is the assumption of the thermal tides as the second most important contributor, if this changes?
Okay, so the first point is that the exchange of angular momentum isn't produced by the radiation pressure or the radiation directly. The actual tool for changing the angular momentum is gravity. It's the sun's gravity acting on the bulge in the atmosphere. Okay, the bulge in the atmosphere is produced by the radiation. So it's a slightly complicated story, right? You heat the atmosphere, that causes the flow of gas horizontally. You get winds moving away from that high temperature spot. That produces a bulge in the atmosphere. But by itself, it doesn't produce any torque at all. Now you got this bulge in the atmosphere. Well, now the sun grabs a hold of that bulge gravitationally, just like it grabs a hold of the ocean bulge gravitationally. Now, in the case of the gravity tides, the bulge is itself caused by gravity. So that's a difference, right? In the thermal tide, the bulge is not caused by gravity. It's caused by the thermal radiation heating the air. But then the torque is actually exerted by gravity, not by radiation. Okay, so that's the first part of the question. The second part was, could you have interactions between the magnetosphere of the Earth and the solar wind, for example, that would produce a torque? And the answer is yes, they could, but I have not calculated them. And I don't know the answer to could they be significant or not. So that's a good question, which I don't have the answer to. So this is, whenever somebody gives a talk, you always got to keep in mind that we have limited imagination. So there could be something I didn't think of. So somebody else thought of that one. So it's probably worth calculating and see if it has an effect. This one became obvious in the 1880s because we could see the barometer going up and down, and then Thomson or Lord Kelvin realized, oh wait, that'll produce a torque. So he's the guy who thought of that.
I also have a very naive question, probably. In one of the plots that you showed the length of the day as a function of time and the three models that you were discussing.
Yeah, I can pull it up. Where was it? The length of the day. There.
Yes, so I realized that you paid a lot of emphasis on the data around 1.5 billion years ago.
Yeah.
But I noticed also that this best fit model that you find doesn't actually find correctly, or doesn't reproduce the gradient or the slope at closer to the present day. So
right.
Yes, and I'm wondering if this is something related to the details of the model, or it has a more profound meaning that you are not finding. You are predicting this again, constant length of the solar day, and then again a decline, which is not seen in the data.
Right. So this is a shortcoming of our model, which has a lot of free parameters. Basically, the free parameter, there's a number of free parameters having to do some with the initial conditions of, what's the actual spin rate of the Earth at a time when the moon was at a given distance, say, 30 Earth radii or whatever. That's one of the initial conditions. That I'm not so worried about. But one of the other parameters is what, in fact, is the resonant period of the atmospheric resonance. And I put it in basically, every 500 million years, I put in a free parameter for that period. Okay. So it ends up the model has, that's 10 free parameters, and I've got another 7. So there's 17 free parameters in this model. And so that's a very high number of free parameters for a model. And we have more than 17 data points. So in that case, we're not going to overfit things. But there's a lot of minima. In fact, well, I'll show you. I didn't emphasize this because these conclusions, I think, are probably somewhat, what I'm trying to get at here is I wouldn't believe the details too much of these best fit curves. Okay. So for example, here's a corner plot. I don't know if you're familiar with looking at these things, but these are the parameters. That's the angular momentum in the Earth Moon system over the present day value. And the labels are too small to read in any case. And then there's the dissipation, the quality factor of the thermal tide. There's the overall normalization of the quality factor of the lunar tide. There's the age of the moon in millions of years or whatever. And then there's all these resonant periods, okay? So there you get fairly robust results, but you can see, for example, here, there's this little black spot next to the main peak. Well, that's another local minimum.
Minimum.
There's more than one solution in this problem because we have so many free parameters. It's a complicated parameter space. So this model, I'm using MC, which is sort of the industry standard MC code in astronomy, which is now 10 or 15 years old, and there are definitely better codes around. And so this is painful. This takes like several weeks to run this Monte Carlo calculation. So I don't think you should believe too much the theory here. I think, like I said, I emphasize the data here is telling you the length of the data is roughly fixed. The details, what you said is correct. There's another, I think I have a plot of the torque. I put the plot of the torque in.
Yes, I was thinking maybe that your best fit solution with all these parameters would be also driven by the data that have also the smaller error bars. And
Yes.
this is why I thought that the more present day measurements would actually drive your best fit solution.
Well, actually, it turns out the data with the smallest error bars is this recent measurement by Myers et al., the green squares. So there's two here very near the present, and then this one that actually has most of the, that's what's driving this thing, trying to get up to that thing. These error bars are probably underestimated. These are from a paper by Mazzullo, this guy, back in '71. He was counting rings, growth rings on clamshells. And I'm pretty sure those error bars are underestimated, actually. Okay, so, you know, the people got excited about this in the 60s and 70s, and then they kind of lost track of it. There's now the much better way of doing the data is looking at these long-term sedimentary deposits, I think. So that's the way forward. And I think, and I'm actually going to propose to go find, because there's a lot more data back in these times, particularly it turns out in Canada, to be explored, because there's a lot of very old rocks in Canada, sedimentary rocks. So we'll get more data back here. So that'll be the really thing to nail down. See, this angular momentum that corresponds to this curve is a lot lower than that angular momentum, and that's the main thing I'd like to go after. Because that says there had to be something to change the angular momentum. And my favorite currently is this thermal tide, but if you can think of other ones, you know, that'd be great.
So I actually have a question about that. I see this point from more 75, which is around 1.5 million years, which is very low.
Right, this one here.
Yeah, and so I understand, okay, these are all data. Has anyone tried to revisit like the analysis or try to reproduce this? And
no,
because this is,
yeah. So at the time, I can go back and tell you. So you can see there's data by Pinelli here, like this yellow dot. It's from 72, and it's got a little S there. So that's a stromatolite data. And more is also stromatolite data from the same deposit, not the exact same stromatolites, but the same geologic deposit. And you can see they got two very different results. One is like 23 hours, and the other one's 20 hours or thereabouts. So those error bars, that error bar I put in from looking at his data, more I used his error bars, which are quite small. Well, these two data points are not consistent, so somebody's error bars are underestimated. You can decide whose. So yeah, this is like, you know, when you first discover some object in astronomy and you've got 3 measurements, well, it's a little better than that. There's, you know, dozens of measurements, but this is not like Sloan Digital Sky Survey data, right? On the other hand, you know, you think it'd be easier to go dig up rocks on the ground, but, you know, it's not so easy.
No, I think this is rather complicated. Yes. Okay. So I don't see any other questions, and we kept you long enough.
Well, thank you for inviting me. It's fun to talk to you about this.
Yes. Thank you. It was a very interesting and unusual talk, I have to say, for our seminar. So yes, thanks for coming.
Yeah.
All right. Thank you very much.
Thank you. Bye.
Bye.
Thank you.
Bye.